And just a small video to show you the principle. We go from copper 1 to copper 2. The copper 2 species is now very happy when it is 5 coordinated. We can again re-inject an electron. It will go back to the 4 coordinate, etc. So this is something which was really at the beginning of this field. To show you that although at the beginning it was very, very slow, we needed seconds to minutes to set the system in motion. But after 10 or 12 years of work, we could prepare very fast-moving systems, rearranging in the microsecond to millisecond time scale. At the same time, exactly at the same time, Professor Stoddart and some of his colleagues made a molecular shuttle, which is kind of a rotaxane again. It can move, as I said before, as a linear motor. So the ring can go from the green station to the red station and go back to the green station. And again, that was the beginning of the field on molecular machines, mostly in Professor Stoddart's group and some other groups. Now, what we have been doing, I'm not going to discuss many systems, but one, which is that of a muscle. Well, of course, it's not a real muscle. This is a bit abusive. But it's a molecular system which can contract and elongate at will. It is a slightly more complex rotaxane. It's a rotaxane dimer. So you have a rotaxane on the top, another rotaxane below, and we have interlinked those two rotaxanes, interconnected those two rotaxanes, so as to obtain a rotaxane dimer. And now we send a chemical signal to the molecule, and the molecule will contract. We go from 8 nanometers to 6 nanometers. We can elongate again, contract again, etc. And this piece of work has inspired many groups who have now developed materials, fibers, which can contract and elongate, and really very exciting systems, more towards applications than the original work we had done at the beginning of the years 2000. Just to tell you that catenanes and rotaxanes are not the only molecules which can be used for making molecular machines. And here are some very important names of people who've either used catenanes and rotaxanes or non-interlocking systems. And I will just show you the work of Ben Feringa and his group at the University of Groningen in the Netherlands. Ben Feringa was working on switches, molecules which you can convert from one form to another form. And they were working on photochemistry of double bonds. So if you have a CC double bond, when you shine light on it, you can isomerize it. And you can isomerize it to another species, an isomer. And they found, more or less by accident, that if you isolate the species which is on the right part, on the upper line, after maybe one night, it rearranges to another species, which is at the bottom now, on the right part. So the system has continued to move. And if you shine light, if you excite photochemically, you will have some motion. You will continue the rotation motion. And finally, by heating, you go back to the starting point. And they published a beautiful video, which I hope will help you to visualize Feringa's chemistry, Feringa's system. So there are 4 steps. The thermal step, a photochemical step, the second thermal step, and a second photochemical step. So now we will start with light. And you see it starts, now you heat, you shine light, you heat, you shine light. And I think the video should show you that it rotates, that it's a one-direction motion. It's a real rotary motor. It's not pirouetting simply. It's a real rotary motor. So can some of you visualize the motion? I hope yes. I'm very sorry if you cannot. I cannot help you. So let me finish up with one of the most complex molecular systems we've made in our group, which is a molecular compressor. So this molecular compressor is a 4-rotaxane. 4, because now the molecule contains 4 molecular fragments, 4 components, which are not covalently speaking interconnected. So there is no covalent bond between any of those 4 components. So this is why it is called a 4-rotaxane. So we have 2 axes at the top and at the bottom. Some people call them dumbbells. And at the middle here. Yeah, sorry. Yeah, you're right, thank you. And now, if you look at the center, you have a bis macrocycle on the right and a bis macrocycle on the left. And in between the 2 rings of each bis macrocycle, you have a plate. The green species is a plate. And the idea, the project, was to check whether we should be able to move the 2 plates and compress something which would be trapped between those 2 plates. So you have G, which is a guest, complex between the 2 green plates, and we will try to find some trick to compress the guest and modify its shape and finally expel it. So this is the project. So now let's look at the molecule. So this is the molecule we wanted to make. This is nothing for the moment but a research project. So we had long discussions in my group. Should we start the project? Should we try to make such a molecule? Because you can easily figure out that it's not a simple project. So we started. You see again, you have the 2 dumbbells, the 2 bis macrocycles, and the 2 plates, which are porphyrins, zinc porphyrins. So we succeeded, and it was much easier than expected because of symmetry and because of the magic template effect of copper. So on top of that, the cherry on the cake, we could even crystallize the molecule and obtain an X-ray structure. And this is the X-ray structure of the species. So it's a relatively heavy molecule, molecular weight of 9,000. And you see the 2 plates. So the plates are those porphyrins at the very center of the molecule. And in between those 2 plates, we can insert molecules, smaller molecules, which can be trapped in between those 2 porphyrins. So till now, the project works. Now, let's try to